All right. Welcome, everybody, to the second session this morning in the general track. My name is Gwen, and I'm chairing this session together with my co-chair, Matthew, over there. And I want to introduce Joanna Piper Morgan, who's going to be talking about MCDC, Monte Carlo Dynamic Code, performant and portable high-performance computing at scale via Python and Numba. Let's give it up for the speaker.
Right. Howdy, everybody. So I'm a mechanical engineer pretending to be a nuclear engineer who has to do a lot of computer science. So hopefully there's something in this talk for everyone. I'm going to start by talking about the actual simulation techniques and some of the physics behind it, because that's what interests me, and we are at a scientific conference. Then we'll talk about MCDC specifically and the design of it and how we're using Numba to do high-performance computing, specifically targeting exaclass, very, very large-scale supercomputers. And then we'll kind of do a general conversation about that structure towards the end. So my affiliations are I'm associated with the Department of Energy, specifically for the NNSA. I'm in a PSAP-3 funded center, which is the Center for Exascale Monte Carlo Neutron Transport, or CEMENT. We have nothing to do with building materials and everything to do with neutrons. We are a consortium of these four illustrious universities, headed up by my home institution, Oregon State, Go Beavs. And we have this little word salad jargon thing as our mission, right? So we're looking to advance the numerical methods of the Monte Carlo method for neutronics, specifically for time-dependent systems, which is something that isn't really done in a full way in a lot of industry codes, on exascale compute architectures, which means CPUs and GPUs, in a sustainable open source way, right? So hopefully by the end of this presentation, you can actually understand what this word salad is. We will return to it. So I want to further motivate my work by talking about this experiment, which is the drag and burst experiment. This was done in 1944 as part of the Manhattan Project, in which a slug of active material falls through this kind of ingot full of other active material, and as the slug falls, we can attain a critical mass, and a reaction can start to occur, right? That reaction is a nuclear chain fission reaction, right, in which heat is released and all different sorts of particles. Before anything bad can happen, though, the slug falls through, stopping the reaction, right? This is a picture of the actual gantry that was used to conduct this experiment, and you actually can't pull that slug back up through because you restart the process. So it does beg the question how they reloaded this thing. Maybe a question for the 1940s OSHA. So let's talk about the fission chain reaction for those of you who don't remember your high school physics. We start with a little neutron, right? And we are always concerned about what this neutron is doing. The reactions that are undergoing are governed by this neutron. If we've done our job as nuclear engineers, we've built a system in which a uranium atom or some other kind of fissionable or fissile material is put in the way of this neutron that is moving at the proper speed. It interacts, releasing daughter elements. These are kind of the radioactive decay elements, a little bit of energy, and crucially, 2 more neutrons. Those neutrons can then, if we've done our job right, slam into more fissionable or fissile material, more energy, more neutrons, more daughter elements, on and on and on and on until you hopefully have a working reactor or a bomb. But what a reactor actually does is controls this population of neutrons, right? We use those control rods to modulate the actual population. We call a critical reactor, which is a reactor of a growth rate of the neutron population of 1, a stable reactor, right? So it's going to constantly produce a constant level of energy. Subcritical, that population of neutrons is decaying. Supercritical, it's growing, right? So really, we are always concerned with what the neutrons are doing. So specifically moving kind of back to this experiment that we're talking about. So this is something that happens really fast, right? In the kind of the blink of an eye, right? This is a log plot on this scale, right? So we're going up 9 orders of magnitude in that burst, right? The energy that's released when that slug falls through is 9 orders of magnitude in the changing of the neutron population and the amount of energy that's released over an insanely small time, over 50 milliseconds, right? So the scale of this problem is insanely difficult to do. If you're trying to model this as a full transient thing using computer simulations, current modern codes have a really hard time as they don't have a lot of numerical methods that are keenly developed to do transient analysis. They're usually more concerned with figuring out those growth rates. So we need new math to be able to actually solve this and model this in a way that is reasonable and understandable. There's a lot of different ways you could solve this kind of problem, right, to actually understand what these populations are going to do. You could develop a nasty governing equation. You could discretize it, using things like backward Euler, and you could solve it deterministically, right? That becomes a giant AX equals B problem that we can solve with LePac. But instead, we're going to use a different technique. We're going to use the Monte Carlo algorithm. So stepping away from our burst problem, this is a slab wall problem, right, where we're going to kind of be curious about if this neutron, same neutron, makes it through this wall. This poor guy's getting just shoved everywhere and shot into everything. So crucially about this problem, we know the material property, right? We have this thing called a cross-section. It's measured. It's from a table, right? And this tells us the probability of interaction of a neutron within a material, right? So it's known, right? We know the geometry, right, the width of this wall, and we have this relationship here, which takes into account a random number, which we're calling C for a given event, divided by that known material cross section, and we can get a distance, right? For those of you who are into statistics, we are sampling from a cumulative probability distribution function. For those of you who aren't fans of statistics, take it on faith. So let's roll a random number. Let's compare. Let's see if that S that we get from that relationship is greater than L. If it is, that's great. We tally it as a transmittance. It could be bad if you're standing on the other side of that wall, but let's say it's great. We do it again, lands inside the wall. That's an absorption event. We tally it. Let's say we do this 6 times. Crucially, that N counter goes up by 6, and we can now actually calculate the transmittance, right? The portion of the neutrons that are going to make it through the wall, right? So it's the number that made it through over the total number, right? So 1/3. Crucially, this is a statistical process. We are doing experimentation, albeit on a computer, but that means that our solutions always have a statistical error associated with it. The more neutrons, the more particles we push, the smaller that statistical error gets, right? But it goes down very slowly, right? We have to push a crap ton of particles to get that to go down to an acceptable level, usually for our purposes. For those of you who are numerical methods people, that error is decreasing by 1 over the square root of n, which is very slow. So that's a Monte Carlo algorithm, but that's kind of the simplest case of a Monte Carlo algorithm. It can get a lot more complicated. So what if the neutrons are going different speeds? What if you're in a 3-dimensional space with both, 3-dimensional position, but as well a 3-dimensional velocity vector, right? So that's 6 independent variables. What if you're modeling through time? That's 7 independent variables, which is that curse of dimensionality is actually usually why we don't like those deterministic problems where we have to discretize. Things get very nasty. So Monte Carlo allows us to kind of avoid a lot of that and kind of handle our 7 independent variables in a much more cognitively less dissonance incurring way. So we have our 7 independent variables. Your neutrons could be going at different speeds. You could have lots of materials. You could have really complicated geometries in these reactors, and on and on and on. And you rue the day that you ever thought, oh, I'll go be a nuclear engineer, because this gets kind of insane, right? So this is a very hard problem to solve. It's a hard problem to solve whatever technique you're using. But when you kind of combine it all together, you can get a Monte Carlo transport solver. We did that in a code called MCDC, Monte Carlo Dynamic Code, which is fully written in Python. And you can see that we can calculate this fission rate, which is kind of like a Geiger counter, right? We're counting how many fission events are happening. You can see it on an XY plot right here, right? So that's as the fission rates through, you can see that slug actually moving through the core. And then this, the figure at your right is actually the term of interest that we have nuclear engineers are most concerned with, which is called flux. You can think of it as a density, the number of neutrons within a given position, within a given unit of time, going in a given direction. So altogether, we can start modeling this really difficult problem in full transientness, right? Crucially, in MCDC, we have technology that can actually model the slug continuously moving, right? As geometries actually move through time. That's the first time that's been implemented in a transport code. Normally, they use stepping functions, which can give you a very rough, which can be very unfortunate to try and use within an effective time rate. For the astute observers of you out there, you might notice that the y-axis on our total burst rate is not 9 orders of magnitude, but only 1. That's because we still have a little bit of evolving to do. There's a pull request that'll probably take us to Charmander in our that I have to do a code review on at some point in the next few days. But we're working up towards being able to do the full 10 to the 9 burst experiment on all of these accelerated hardwares. So that's kind of the introduction and the physics component. So what are our major takeaways? That problem was not a linear algebra problem, right? That's bad for us because if it was a linear algebra problem, we could use CuPy, we could use SciPy, we could use LPAC, we could use sundials, we could use whatever we wanted, but we can't, right? The actual numerical methods and the physics are happening in the same compute kernels, right? That you cannot divorce them, right? So if you have a person who's working on those numerical methods, they also have to be working in kernels that will be compiled to whatever hardware target you're working in, right? Each particle history is completely independent of the other particles, right? So that means that's where our parallelism is coming from, right? We don't have to consider where all of, if we don't have to model a certain number of particles at once, we can model all 6 in unison if we wanted to, from that previous example. If we wanted to model 10,000 particles, we can model 10,000 particles at once. So that's where we're getting our parallelism. It doesn't matter if it's shared memory, like OpenMP type parallelism, distributed memory, like MPI type parallelism, or if you're on a GPU, right? It's the same kind of structure. Our solutions always have a statistical error, and that error converges very slowly. We need to move a lot of particles to be able to get a solution in our entire phase space, right? Millions, billions, trillions, gajillions, on and on and on, right? If you have a meters by meters scale problem and you have a millimeter by millimeter sized mesh, you need particles from whatever your source is to stream through that, right? The likelihood of that happening is very, very low. So you need to jack up the number of particles so that not only that it happens, but it happens multiple times so that you can have a well-defined solution in that area. So really this kind of leads that we will need every single flop, every single computing resource we can get our little paws on, right? This is a problem that demands the exascale, that demands GPUs, that demands whatever the cutting edge is. Historically, these algorithms have actually sat at high performance computing since high performance computing began with ENIAC in the 40s, right? So the Monte Carlo method was actually invented as part of the Manhattan Project. So, so that's kind of where we're sitting, right? So a lot of traditional development has been done over the decades in these huge codes that exist at the national labs. A lot of them are export controlled. There's 1 or 2 that are open source, but we're talking about hundreds of thousands of lines. We're talking about really insanely complicated control flow. We're talking about different kernel sets for each hardware accelerator, whether you're running on x86 CPUs or AMD or NVIDIA GPUs, right? So we want to kind of be able to simplify that for our developers, right? And have a single set of kernels, right, that can be compiled via any structure to any hardware target, right? So our modern HPCs use a lot of those GPUs, right? So we need to be able to compile to that. So this kind of leads to a location where we're curious about performance portability frameworks. Some of the big name brands are Cocos and Raja. There's other ones that have been experimented through various codes over the years. A domain-specific language paired with Python as a glue, right, has been pretty successful in a lot of in a few CFD applications. Julia is kind of the one everyone's talking about, and the one that's very hot on the scene right now. But we focused in first on Numba. Numba is a wrapper for LLVM, is kind of the best way to think about it, right? It's actually a subset of Python. You can kind of think of it as that subset of Python as a Python-based DSL, right? So that gets performantly compiled at runtime. It's a JIT compiler, right? So you will have to pay JIT compiler overhead. On CPUs, we use MPI4Pi to do all of our threading, so we actually don't do any shared memory parallelism within Numba. It's all through MPI4Pi, and then together that makes MCDC. So the layout of kind of how the code works when you're to execute something, you start with a user-defined input, right? So this is where that user is defining the geometry, those material cross-sections, what's happening through time, the parameters of interest that I want to tally on, that I want to actually have information on. And at the end, they call mcdc.run. So that script executes, calls mcdc.run, that calls our input deck builder, right? So this conditions all the inputs, makes sure you're not doing anything funky with negative numbers, and then builds our data type. Our data type is static in this case, right? So we allocate it as one giant numpy ND array at the beginning. That gets passed around to all of our functions. That's built here. Main.py is then where we're doing all of the like inputs and outputs. This is where we're launching our MPI threads and beginning and ending our computation. So when the actual computation begins, we distribute to however many threads you're running within your Numba mode. And from here on out, all of the actual Python script has been compiled using Numba, right? So loop.py contains kind of our overall logic for this problem, right? So like the thing that's actually saying, do this, then do that, then do that. That's in loop.py because that describes an actual algorithm. And then kernel.py is, our very simple rudimentary functions that are moving particles or something. At the end, you can use h5 for pi and have a nice output that can then be visualized using another script. So what this looks like when you're actually compiling something, we use the ngit decorator around all of our functions that are to be compiled. So you can see that these are examples of our actual kernels, right? So you have move particle. It's fairly simple, right? Vector calc, kind of stuff right there. And then the second figure is an example of our particle data type, right? So we're using a numpy nd array, right, to allocate our particle buckets, our particle bins, our cross-section data, and all that. And then you can actually see how we index it, right? And you're able to actually call out by name specific terms within the nd array to make it a little more workable. You don't have to remember offsets or something like that. Everything's just-in-time compilation, right? So you do have to pay the piper on that one, but it's usually for large, sufficiently programmable, sufficient problems. It's pretty negligible, about 1.5 minutes for most problems. One thing to note about Numba is that it does support numpy operations on the CPU side, but on the GPU side, it supports pretty much only arithmetic operations. So because we actually like to compile the same set of kernels for CPU and GPU, we can only use the CPU set of functions for most of our kernels. So that's kind of a hiccup for us. So some performance results would be nice. This is a different kind of time-dependent problem. This is called the Kobayashi dog-leg void problem, in which we're going to release some energy, like a burst of neutrons at time t equals 0. It's going to move down a void path and interact with fissionable material through time, right? So I'm really bad at art, but I always wanted to make pretty pictures, so that's why I'm in this. So this is runtime. This is a table of runtime and then something called figure of merit. Figure of merit is a term that takes into account both that statistical error from the Monte Carlo solution along with the actual runtime itself. So higher is better for figure of merit. OpenMC is the other major open source Monte Carlo, I will dare not call us major, but is the other open source Monte Carlo neutronics software that's out there, and does have some capability for time-dependent problems. But you can see all this static and noise because that's not their goal. Their goal isn't to do time-dependent problems, so they've made design choices that makes it less amenable for that. So MCDC is slower than most traditionally compiled codes, usually on the order of 2 to 10 times, and we've compared against a lot of different production codes for a few different problem types. But you can see that we have this MCDC and then MCDC new, right? And this is kind of the big deal about why we did this, right? Is really we're curious about rapidly implementing and developing numerical methods to solve these difficult time-dependent problems, right? So you can see that figure of merit goes from 2.24 to 7.32, right? And our runtime is decreased by almost 3/4, right? Still slower than OpenMC, right? Still slower than a full-fledged production code, but we're in the same ballpark, right? We are in the same region maybe of performance, and we are getting a much better solution out of our simulation, right? So what happened between here, right? Postdocs said, hey, I think we can improve our tally structure. A grad student said, oh my gosh, yeah, I think I can do that. And about a half a day's worth of work goes in, and we see these incredible runtimes, right? Because we're able to change, really key components of the simulation, very rapidly, right? Nothing is very rigid because we're using this just-in-time compilation scheme. If we want to make major code, like rip out major parts of the code, it's fairly simple to do that to solve certain specific problems, or to collaborate and actually push things back up into our GitHub and make really good pull requests and do good code review. We can do that as well, right? So this is about a half a day's of work of collaboration within our open source community, right? Being able to do, and this is really like, when I evangelize this project, this is what we're talking about, right? That this is kind of that rapid methods development scheme that we can really start to explore new and novel things here. So we do support compilation to GPUs. Unfortunately, on GPUs, we can't ensure everything is going to be executing serially within a thread, right? GPUs have a much different parallelism paradigm. So for things like an array addition, right, we need to make sure that we're doing an atomic add call to the API, right? So we can do that with simple Python abstraction decorators, so that if you have a function that's going to call something like this, you just call one of these decorators, and then it can change it at runtime. Just because code can compile and execute on a GPU doesn't mean it should. The Monte Carlo process, as we like to program it, is what we call very divergent, which is fine on CPUs, right? If I produce two neutrons that are sitting right next to each other, one might go left, one might go right. What is left in a reactor might look very different than what is right. So different sets of functions have to be called. We use something called Harmonize to do on-the-fly event scheduling. I'm not going to talk any more about that. I'm going to leave you with bated breath and tempest heart and tell you to go to my colleague's talk tomorrow. Braxton, his figures make your mouth water, so I would encourage anyone to do it. But when we do it, this is a full node of, so we're running on 2 Xeon CPUs compared to 1 Tesla V100, so even kind of an older GPU at this point. We're not even saturating up to 1 billion particles, and we see 21 to 24 times speed up, right, over that full node. This is on par with what production codes get when they move to GPUs. So very cool work. It's amazing that this works. I can't tell you how cool this is to see it, and how nice it is to have these problems compute very quickly. If you're curious more about the research components, feel free to check out our article on JOS. Also, I would huge call out to all of my colleagues. This is very much a team effort. So citation where citation is due. So briefly before I conclude, I just wanted to mention some limitations of Numba. So if you're in the audience and you're like, ooh, I can do an exa-class compute app on CPUs and GPUs and get it working right away, it's still really difficult to do this kind of work. And you kind of you're making Faustian bargains, right? So there's a lot of C-side things within Numba. So if you're in a compiled function that don't work, a big one for us is MPI calls, right? So there's ways to work around that, but they can be clunky and limit performance. There can be long compile times. We care about intermediate compiler representations for a lot of the work we do. So the documentation on what we're actually getting from Numba can be not as good as we would hope. Right now it's lacking ahead of time compilation. I know that there's a lot of work being done to improve that. And then cryptic compiler errors. And debugging with this is kind of a nightmare, as compared to debugging in like a C++ application. You might be asking, Piper, how much of a nightmare is it? Well, and it just keeps going, and on and on and on. This is if you change a data type to what is unexpected, right? So if you were compiling using Clang or something, it'd be one line, it'd be like, hey, I think you screwed up a double, but you get this kind of a mess. There are other things out there that also do this work. Some research has shown that it's more performant. There's this paper by a researcher at Oak Ridge who has a lot of very interesting perspectives on this kind of work. If you are really mindful about performance and you're in a floppy bound problem, maybe one of these might be more what you're looking for. I think if we were to redo this, we might give Julia a much harder look. We started this project about 5 years ago, so Julia had no GPU compute capabilities. Now it has a lot, maybe even more than Numba. I haven't really evaluated it for myself, but it does support allegedly more actual architecture or more GPU vendors. So we have a lot of current and ongoing work. The biggest one is getting support for AMD, right? Who uses an AMD GPU? Well, we do, because that's what the exa-class computers are actually using. They're using MI250Xs, which is an AMD architecture. So being able to compile to AMD is what we're kind of working on right now. We're pretty close, we think, so hopefully within the next 3 months we'll have some interesting results and be able to do a nice little horse race between red and green. So just in conclusions, I hope when you read this statement now, you understand what we're doing, why it's hard, why we need the exascale, why we're using Python to do it, right? We are really strongly curious about doing rapid methods development and working in a team dynamic that is collaborative and that is open, right? And for us, a really good way of doing that is by working in Python. Monte Carlo neutron transport is insanely hard. Exoclass computing is insanely hard. But performance portability framework, specifically using Numba, for us, we believe has allowed us to make insane progress in very, very short amounts of time. So thank you very much for your attention. That is the conclusion of my talk. I will now take your questions.
Thank you so much for a great talk. All right, I'm going to take some questions from the audience. Please raise your hand. Yep.
Thank you so much for that wonderful talk. You touched briefly upon the AMD components of this, and can you give us a little bit more in terms of how you're adding that capability? Because Numba typically is focused on the CUDA side.
Thank you so much. Thank you. So AMD's entire compiler stack is Clang-based, right? So if you call hipcc, it's actually a wrapper for Clang. So Numba is an LLVM project with bindings. So it, theoretically, it could happen. I have some NDAs personally, so I can't, get too far into the weeds on that specific topic. But that's kind of. Right, everything's IR, right? Everything's an intermediate representation. So if you just pipe it to the right place and you make the right function calls, you should be able to produce it.
So very nice talk. Full disclosure, I'm a Numba developer. So I've actually just sent the team your Numba limitation slide. So thank you for putting that up. I don't want to freak people out, but we love getting that feedback because it's hard to tell in the infinite space of compilers what people are struggling with. I'm also very interested in that AMD thing. I don't know if I can get in on those NDAs, but feel free to chat afterwards. I did have, oh shoot, I forgot what the question was. Anyway, is the source code for this available somewhere that we can look at it? We love seeing how people use Numba in practice in the wild.
I just always get so excited because I'm a nuclear engineer, which means everything is behind a paywall or is export controlled or is classified. But this is not. There's a GitHub. If you go to that JOS paper, then that'll go to our GitHub. We have a pip installable package potentially. It might not work with Numba, so you could pip install MCDC. It may or may not work, but feel free to take a look. I have a lot more. I'd love to chat further about Numba and our experience, especially, and it, the fact it works is, I remember, I think, I really got into performance work because I saw Numba work years ago. In my first year of my PhD, I was like, wow, look at my crappy little finite difference code just ran in 2 seconds instead of an hour. That's amazing. So thank you for the development is what I'm trying to say.
Thank you.
Hi, great talk first. So you mentioned that you're not using Numba parallelization, the built-in ones. So you're using MPI for Pi. So can you elaborate more on why that decision and also how hard, easy it is?
So that's a pretty standard decision in my field. Is that instead of doing shared memory parallelism, everyone just opts in for MPI, distributed type memory parallelism, because you will have to have MPI. You don't necessarily have to have shared, right? So just do MPI, and maybe we might come back later to shared memory parallelism because we are leaving a lot of performance on the table for that. So I think the person who does a lot of the MPI work, is Braxton, and then also we have another professor who works on this, and a few of the other grad students. So they'll probably be able to elaborate more, but effectively each thread is going to go through the compilation process. So each thread, so you make your function call on the MPI thread, right? So you're distributing the compilation as well as the actual work of your thing, and then they can communicate within an iteration, but you have to do that through object moding, which can be really, if you have 10,000 MPI processes, if one of those fails for whatever reason, then your entire program fails. So an object mode we've found to be pretty hit or miss as far as supportability. So.
A quick follow-up question on that. How do you handle like error logging and kind of the status of your experiment?
GitHub issues. Yeah, so it's up on GitHub. So if you want to see a bunch of people muddling through, cursing, and trying to really struggle through something, check out our GitHub issues. We also have a Slack, so if it's more of an urgent thing, internal to our project, like somebody's trying to get some research done before their master's or whatever, then we'll handle it there. But issue tracking is like, I think that's a big one that we still like every time we have a meeting, I'm always like, did you put that in a GitHub issue maybe? Can you put that up there, so we can track it? But yeah.
Great. Thank you so much. We are out of time, but please feel free to walk up and talk to the speaker. Let's thank her again for the great talk. Thank you so much.